Production ML systems live or die by processing millions of simultaneous, sparse interactions. Ingestion pipelines are constantly bombarded with high-velocity behavioral logs. The standard engineering failure point here is trying to represent categorical data, like user IDs or an ever-changing product catalog with one hot encoding. It is mathematically wasteful. If you have 10 million users, every individual user is represented as a 10 million dimensional vector containing entirely zeros except for a single one marking their exact position. Worse, this structure is incapable of generalizing. When a brand new user arrives, they have never appeared in your training data, which means they share no parameters with existing users. You need a new dimension and a newly trained model just to interact with them. Embeddings solve sparsity by functioning as a mathematical bottleneck. We compress that massive grid of ones and zeros down into a dense range of floating point numbers. Constraining this space forces the model to approximate, mapping similar behaviors into proximate geometric coordinates. Embeddings are an enforced representation shift. They strip away isolated IDs and mandate that the model learns underlying structural relationships. During system design interviews, it is common to hear embeddings described through hand-wavy appeals to semantic understanding or by quoting standard word-to-vec analogies. In a production context, embeddings do not possess inherent semantic magic. Their geometric clustering is an artificial construct, dictated entirely by the explicit architectural choices made during training. To understand how this geometry is truly formed, we need to engineer a production-grade embedding system from first principles. We will start with the baseline of matrix factorization, evolve into a two-tower neural architecture, and finally deploy the system for sub-100 millisecond global retrieval. Understanding the strict mathematical constraints of an embedding space is the only way an engineer can reliably scale similarity search in production. We begin with matrix factorization, the classical transductive baseline for learning dense representations directly from behavioral logs. Look at this 2D interaction matrix, labeled R. We have 100 million users on the y-axis and 10,000 items on the x-axis. Cells are populated only where a user interacted with an item, leaving the vast majority of the grid completely empty. The core mathematical objective here is to decompose matrix R into two smaller, dense matrices. We create matrix U for users and matrix V transpose for items. When you multiply a specific user row from matrix U by an item column from V transpose, the resulting dot product approximates the corresponding cell in the original matrix R. Forcing 100 million complex interactions into a shared 64-dimensional rank means the system cannot afford to give every user a completely unique identity. This low rank constraint drives the discovery of shared patterns. Groups with highly correlated behaviors, like late-night sci-fi watchers, naturally cluster into similar rows within matrix U. Yet, matrix factorization carries a critical failure point, the cold start problem. Because this is a transductive method, it relies on a fixed lookup table. A brand new user or video requires an entirely new row or column, which mandates a full system retrain before they can be embedded. Matrix factorization proves the viability of low-rank mathematical compression, but its inability to embed new entities dynamically makes it unsuitable for real-time scale. To solve the cold start limitation and ingest rich metadata, modern systems rely on a decoupled paradigm, the two-tower architecture. This diagram outlines the architecture's two prongs. The left side is the query tower. It processes dynamic user context, like demographics and recent watch history, passing it through a multi-layer perceptron. In parallel, the right side is the candidate tower. It ingests static item features, text metadata, video categories, and title strings, often passing them through a transformer. These are distinct neural networks, yet both towers output their final calculations into the exact same shared geometric vector space. This creates a strict engineering rule. Despite processing completely different inputs, dimension 7 in the user embedding must mathematically align with the exact same latent concept in the item embedding's dimension 7. This setup solves the cold start problem. Because embeddings are generated by passing features through a function rather than reading from a static table, brand new items can be accurately embedded on the fly at inference time. The two-tower model transitions embeddings from a rigid map of past interactions into a predictive engine, capable of placing entirely new entities into an existing universe. How did two entirely separate neural networks learn to map their vectors into the exact same coordinate space without being explicitly given categories to sort into? The explicit training mechanism is contrastive learning, which relies on known positive pairs and known negative pairs sourced directly from behavioral logs. We execute this using loss functions like triplet loss or ENFO-NCE. This visual shows a minimalist 3D coordinate space with an anchor point, a positive point, and a negative point. The mathematical force of the loss function kicks in. The anchor point acts like a magnet, pulling the positive point closer, while simultaneously repelling the negative point outward. To prevent the model from learning trivial distinctions, engineers perform rigorous negative sampling. Finding hard negatives, items the model incorrectly thinks are relevant, forces the network to learn deeper features. In this space, the reality of similarity is entirely dictated by the specific objective function you choose, not by inherent semantic traits. A model trained on a co-purchase objective will cluster toothbrushes and toothpaste tightly together. A model trained on a co-watch objective will cluster visually distinct but behaviorally paired late-night videos. An embedding's geometry is never accidental. It is a strict, self-organizing reflection of the exact loss constraints configured by the engineer. Moving from the theoretical training environment to the reality of production requires executing this similarity search across billions of items in under 100 milliseconds. Running a live neural network forward pass on every possible user item combination at query time is computationally impossible. Here is the serving advantage of the two-tower decoupling. Candidate embeddings are pre-computed offline and loaded into an approximate nearest neighbor index. When a live query hits, the query tower generates a single vector, performing rapid search against the index. Shifting the heavy computational burden to asynchronous offline indexing is the definitive architectural pattern that makes modern global retrieval, recommendation, and RAG systems viable at scale. Managing this scale uncovers a hidden operational cost. Vectors go stale. As user behavior drifts and inventory changes over time, the embedding space degrades. Mitigating this drift requires extensive infrastructure, ranging from nightly scheduled batch recalculations to aggressive near real-time updates served directly out of parameter servers. Finally, engineers must navigate evaluation. During system design, you should discard academic, intrinsic evaluation methods, like checking for word analogies. Extrinsic evaluation is the gold standard. The embedding is measured exclusively by its performance on downstream tasks, relying on metrics like recall at K for retrieval systems. An embedding is never measured by how beautifully it clusters abstractions. It is measured entirely by how efficiently it drives the final production metric.